So all we need to calculate is this. In order to calculate that, we need to have information about this, and we know that at least this x of t is nothing but solution of this SDE. And now I can ask you the question, how can I solve this SDE? So one way is going to be you just calculate A1, like A2, and then B1, 0, B2 to be mu, sigma, and you apply everything, and then you will get something. Okay. Hello. Hello.
Hello.
Yes, you're here. Hello. Message जो था भी 1 minute. Okay. Karen ang hindi yan. Prepare sa award. Patna कर रहे. Kal पैसा नहीं था. Record this. Zoom record. Continue. Yeah. So like we need to calculate this. In order to calculate this, we need to have information about x of t, and all we know about this is this x of t is solution of this is d. Fine. Now I have given
Yeah.
this instruction that one way is going to be you take this A1, A2, B1, B2, and then apply and repeat the procedure that we have done recently. Okay.
Mm-hmm.
But the other thing is I told also one other point to you that if you want to solve this as the dxt equal to mu dt plus sigma dwt in this way, that with this dt you don't have this x like this one, and with this dwt you don't have this x of t. If you have such scenario, then you don't need to go for this a1, a2, b1, b2. So this is a particular scenario I am considering.
Mm-hmm.
Particular scenario I am just throwing out that if your SD is in a form that you don't have x multiplied with this dt, and in other words, I am saying that if your a1 is 0 and also b1 is 0. So let's say this way, if your a1 and b1 are 0, then you just integrate this both sides at this place.
Mm-hmm.
So like you integrate
Right.
is now integrating matters from where to where we are integrating. Like we want to integrate it from 0 to t or from t naught to t. So let's for the moment let's integrate it from t to this capital T dxt dxs equal to t to capital T mu dt ds, sorry, plus t to capital T sigma dws. So when you integrate this, you will get x of t minus xt. This mu is constant, so this is going to be t minus t, plus this sigma is constant, so this dw is basically dB. Sorry, this is dB in your case. It's going to be beta t minus b small t, or my x of t is going to be x of t plus mu times t minus t plus sigma times b t minus b t. You okay with this? Like
Yeah.
till this. So now this is my
Yeah.
random variable. This is my random variable. This is the random variable. And so you see that this beta is normally distributed. You know this.
Uh,
Beta is kind of Brownian, and Brownian is normally distributed with mean
okay,
0
fine.
and variance t, right?
Mhm.
So with the help of that, it's kind of your assignment. And if you can't, then I'll tell you that if you take its expectation, then the expectation turns out to be x plus mu times t minus t. You maybe just apply this. Yeah, so here is the multiplication. Why this is the multiplication? Why this
Right.
is the multiplication? This shouldn't be multiplication. This should be plus. Like in your solution manual, he was giving multiplication. Ah, that's why I was saying that last day we were confused. Oh no, shit. So you just multiply expectation. When you will multiply expectation, this guy has zero expectation. This guy also has because they are Brownian. So you will left with this.
Yeah, fine.
Yeah. So
Because
expectation is this. Yeah. And you also need variance of this x of t. When you apply
mm-hmm.
variance on all of this, so this is xt, and this xt is kind of you can say that this is kind of you are treating it at a point t. So like it is also for you here it is constant. We need to write it as x of maybe t naught so that this really looks like constant uh, at a fixed point, like x at a fixed point. So this is constant. You have to treat it like constant. You're getting me why?
Yeah.
Yeah, because I have integrated from t to capital T. If you integrate from 0 to t, so this was x naught basically. So like it's in that way it's kind of constant. If you apply that this guy bt minus bt, and then you take this variance. I told you last day one property of variance that it eats up this constant thing.
Yeah.
This property variance of ax plus b was equal to, just as b will go away, a square variance of x. So this will square this constant sigma square and then variance of this bt minus bt. And from the properties of Brownian, we already know that this is going to be sigma square t minus t. So variance is going to be this. So therefore my x of t is normally distributed with expectation, or we say with mean this mu times t minus t, and with variance sigma square t minus t. So this is the information about x of t, that x of t is basically normally distributed function, normally distributed random variable with this mean and this variance. So this is mean and this is variance, and this is my
Wait,
x
so
of
where did the
yeah, yeah,
Feynman Kac?
yeah. I told you that Feynman Kac said that if you want to solve this PDE, this kind of PDE,
Yeah.
you need to solve this SD. Okay,
Okay, fine, fine,
and
fine.
whatever the solution is, you have to calculate that solution at this initial condition, in other words phi of x. Then you apply expectation and then you this take. So you
Okay.
need to have information about this x of t from here. So that's why I solved this SDE, and I got this solution x of t, and I also checked that this x of t is normally distributed with mean this and variance this.
Fine, fine, fine.
Fine. So now come to this e to the x of t given ft. What should be this? How to calculate this?
Hmm.
So do you know anything about MGF, moment generating function?
Yeah.
So let me show you one relationship. So read this carefully. He's writing here. Read this carefully. Read this line. What is saying? That moment generating function for a random variable can be used to calculate all of the moments of the variable. It is also defined as the expectation of an exponential function of that variable. So if you even keep this, again, this is expectation. So this is nothing but this is going to be a moment generating function at this x of t. So it's like it's going to be equal to MGF, moment generating function, because we are taking the exponential of random variable.
Yeah.
And now if I know the MGF, in other words, moment generating function, then I know this. Like I just calculate this moment generating function of this x of t. Whatever it is going to be equal to this by this property.
Sure.
Okay. So let's see. Let me take you to, even now I'll not waste my more time in order to have this clear. So now I have taken you to the solution that you sent me. So now that it says that using moment generating function of normal random variable, this is the moment generating function of normal random variable, MGF of this x of t. This is MGF of x. So this is moment generating function of x of t. So this must be equal to expectation of e to the xt given ft, which is this. So this is going to be solution to the PDE that we had. This, sorry. Yeah. Now you ask me question. Now you can ask that where did this come from? Like,
Mm-hmm.
so yeah, I can answer it. That's not a big deal. Yeah, I'll answer this. Okay. So let me, so one thing that we know that our random variable is normal. Okay.
Mm-hmm.
One thing that we know is our random variable is normal. And distribution. So MGF of the normal distribution is this.
Right.
Okay, so I'm telling you that this is MGF of normal distribution. Okay, this guy over here. This guy over here is going to be the MGF of normal distribution. So let me write it. Okay, so let me take you to this. All I need is I need MGF of normal, MGF of this x of t. I know that this is normally distributed, and for normally distributed uh, random variable, my MGF is f of x equal to e to the r m of t equal to e to the mean. I'm writing in words, mean multiplied by time plus 1 over 2 variance times variance time t.
Mm-hmm.
So you can say, see this like here. So this is mean, this is variance times t square. Sorry, I didn't put the square there. Okay, so let me put a square there. You didn't see that I was there. Yeah, there. You see this? This is the
Yeah.
moment
Yeah. Yeah. Yeah.
generating function of normal distributed, and this is mean, this is variance, this is square.
Yeah.
So now let's come back to this over here. So we will write our moment generating function m of t equal to e to the, what was mean of our random variable? The mean of our random variable is going to be this x plus mu times t minus t. X plus mu times capital T minus t. Okay.
Yeah.
Yeah. So, okay, just a second. Right. Plus 1 over 2. So this is variance, like this is variance. So sigma times sigma square times t minus t, like this way. So this is going to be my MGF for our case. So like you have to further like you have to work on this further, that x of t was normally distributed with mean and variance. So what is its MGF, moment generating function? Once you have calculated moment generating function, so that is going to be equal to this guy, expectation of this this guy, expectation of e to the xt given ft is equal to moment generating function of this x of t. So this is basically e to the x plus mu times t minus t plus 1 over 2 sigma square t minus t, right? So you have to kind of research it a bit, that you have to make sure that it is like this is it. You have to make sure it. So I'm leaving it for you. You just
Right.
need to
Yeah.
make sure that this is going to be MGF. You have to make sure this thing, that if your random variable is x of t, which is normally distributed with this mean t minus t and with this variance sigma square t minus t, then its MGF is going to be equal to this. You just have to make sure this, like this is
Yep.
going maybe over 2, I don't know. Yeah, maybe over 2 just confirm.
Yeah.
Yeah, over 2. Yeah, so yeah, this is here. So he has used this concept. This is here. Okay. I think we will have one more session. It's already 2 hours.
Okay, fine. Yeah, sure.
In the next session, we will cover this question 7, inshallah, and then question 3 also.
Inshallah, yeah.
Yeah.